The talk is going to be about how to talk to your pipeline. So how to use large language models to make dynamic transformations based on user questions while the pipeline is still running. So Beam is great for inference. So writing a streaming pipeline for inference, it's super easy. But beyond just calling a single model, so what does it mean that we can do real-time inference? So this simplicity opens lots of doors to doing really cool stuff. So and this is, we're going to see an example of this today here. So this talk is brought to you by myself. I work in Google Cloud as a data engineer, and by Fear, my colleague, also from Google Cloud, in the Tel Aviv office. He couldn't be here today, so but this is joint work between the both of us. And this is something that we've been working with a customer in the field. The agenda for today, so we're going to be covering first what are the goodies that Beam has for ML and AI, the so-called turnkey transforms. Then we're going to think of how we should prepare our data for a dynamic transformation. In Beam, once you write a pipeline, it's a static thing. You cannot change it. So how we can make the pipeline do different transformations based on the input, based on the questions. We're going to see what's the role here of side inputs for the patterns that we're going to explain here, with a few advices and comments about how to leverage side inputs in the right way to enable these dynamic transformations based on the user questions. And we will wrap up with some conclusions and a couple of repositories if you want to play with the examples that we have prepared. So Beam ML. Beam comes with a lot of transformations, with a few transformations for simplifying doing ML workloads. Here we are talking only of run inference, but this is not the only one. So there are a few others also for feature engineering and for a few other things. Run inference, what is it? It is. So you have already probably seen it in other talks. It's just a way for, in a very simple way, call a model from a pipeline in Apache Beam. So in streaming, in batch, wherever. So here we have a documentation from, an example from the documentation of Apache Beam of how to use a PyTorch model that is stored in Google Cloud Storage to do some predictions and, well, post-process those predictions. Very typical example. What can you do with run inference? Well, you can use it for local models. Like, for instance, again, so the example that we have just seen is it's a local model. The model is in cloud storage, but gets downloaded locally into the worker. It gets loaded in memory. If there is the GPU, it will probably use a GPU. So there are many ways to leverage the local hardware to run a local model. TensorFlow, either the model is in TensorFlow, PyTorch. If it's a large language model, you can also use VLLM to run the inference. And there's a talk about this, I think, after this one. Scikit-learn. There are probably a few other examples. Here, for instance, we have one of the examples from the Dataflow documentation on how to run a model to do a translation from English to Spanish. The notebook is in this link. It's a Dataflow documentation, but it's a generic Beam pipeline. You could run it anywhere, not necessarily only in Dataflow. So if you have tried running a local model in a streaming pipeline specifically, it's a total pain. Okay, so streaming pipeline will have a very high degree of parallelization to try to make a good use of the resources in your cluster of workers that you're using. So using run inference makes it super simple to make the best use of these resources, even if you're running a large model. So typically, because of the high degree of parallelization, there will be some duplication of objects in memory. You will be loading the same stuff a lot of times, even if you're not aware of it, because of just, let's say, how physically the pipeline is executed. If you're using run inference, you don't have to worry about this. Basically, run inference will make a good choice of just running the model once in memory and trying to reuse it as much as possible across all the processes, all the threads that are running in your worker, because a model can be really something huge. In the repository that I will be sharing at the end of this talk, we are using, for instance, Gemma 3. Gemma 3, which is with the model of I don't remember now how many billion parameters it has, but it's a few gigabytes object, because really it's large, okay? You don't want to load that in memory like 4 or 5 times if you have 4 or 5 CPUs. You want to load it once and reuse it as much as possible. So local models, problem solved. What about remote models? This is even easier. So either if your model is in Hugging Face or TensorFlow Hub, it is deployed as a Vertex endpoint, it is Gemini, and a few other examples. It's super easy to use with run inference. You don't have to worry about batching your request or handling errors and retries, and these kind of things that are typical when you are accessing an external API and which are a total pain. So again, this is also something that run inference takes care for you. So here, for instance, we have an example of using Gemini with Google AI Studio very easily. So the most complex situation that you can have with a remote model is that you have to write a custom handler because, because I don't know, your particular API model between codes, it could be any API actually, anything that you can call, so might not be supported by default or yet by run inference. So what does it take to create a custom handler? So here we have an example, again extracted from the Cloud Data Flow documentation, but it's completely generic, it's just been, that is using the Cloud Vision API, which is a model, right? So because, well, there's some kind of model behind that API, right? To do some image classification. So this is all that it takes to create a handler, okay? So count the number of lines of code that are here. I haven't counted, but it's, I don't know, like 10, 20, not more, okay? And it's actually almost copy-paste. If you have a way to initialize your client, and you have a way to use your client to call it with some input data and to get the output, that's all that you need to know. Everything else is taken care of. So it's super easy. And finally, and it looks like I'm selling here run inference. I really like it, really. So it made my life much easier, and it's a pleasure to do inference with it, being now with it. So finally, if you have more complex stuff, I don't know, like ensemble models. You want to run several models, and then with the output of all these models, make a decision about what is going to be the prediction. Or you want to do, I don't know, A/B testing, or these kind of things. These are patterns of that, because it's so simple to use run inference, they are simple to implement in Min, even though they are, let's say, conceptually complex. Okay, so enough of run inference. So the takeaway is run inference is easy to use, and because it's easy to use, it enables lots of use cases, and I would say the limit here is imagination. So let's talk about one of these use cases. So let's try to talk about our pipelines. Let's talk to our pipelines to make them execute dynamic transformations. Let's wait here. Let's stop here for a second. So a pipeline is something static. If you want your pipeline to run some kind of execution, some kind of transformation, you need to know that transformation in advance, because you need to encode that in the pipeline before it's deployed, before it's run. So how can we make a transformation that is dynamic if we need to fulfill this requirement? Well, if we prepare the data in specific ways, so we can actually take code as output of an LLM and run it in our pipeline. So let's talk about this condition, about data preparation for dynamic transformations. The first thing that we need to do is we need to remember that our data needs to be processed per key. And we also need to apply a window. So basically, it's two conditions: per key processing and apply a window. And this is, in summary, because we need to have some boundaries for the context of the calculation. And we will see later why. So this is important. Context is the key here. So the partitioning is required also because the context imposes a vertical limit on the amount of data that we can apply a particular transformation to. So we're going to be applying the transformation per key, and each one of the keys should be small enough. Now, this key for the data processing defines the partitioning for our calculation. For instance, the example that is in the repo that I will be sharing at the end, so we are having some gain activity, and the only kind of questions that we can answer dynamically is questions that are referred or partitioned by user ID. So which is the user with the highest score? Which is the user with the longest streak? Which is the user that spent the most in the last week? These kind of questions, okay? So the key defines the kind of question. So this is a limitation. We can do dynamic transformations, but not any kind of transformation. So here partitioning per key. And then the window, again, we are in streaming. For how long do we need to wait until we are able to answer a question? So for instance, so do I want to, if I want to know where is the user with the highest spend, so well, this needs to be done in a certain time context. And for this, I also need to define a window. And the window is going to be important also because in a streaming, if I want to join somehow the question with the data, the question will also have to have a window, but we will cover more about that later. So basically, again, two conditions that we need to meet here. So we need to have a processing key, and we need to have a window, okay? And this is how the pipeline looks like conceptually. So this is the logical pipeline, the static pipeline. So we get data. In this case, for instance, we extract the user ID in the example of the game. So we have a tuple with user ID and data. The user ID is the key, data is the value. We apply a window, wherever window is that, and then we group. And then we are going to generate the prompt with this group. And the question is here put into the prompt as a side input, okay? And then the output of the prompting, the output of the run inference with the LLM is some code that we can execute, and we will see later how we execute it. Great, let's talk about side inputs. So side inputs are used here for two things. One, we just saw, is the ingestion of the question into the prompt. And the other one, another important role here for side inputs, is the execution of the code. So the questions here, like the questions are the crucial part of this pipeline. So we want the pipeline to be able to answer generic questions in natural language. People want to make questions to the data. This is something that you can do now in data warehouses. Anyone can go and make a question in natural language, and the data warehouse, like BigQuery or whatever, may figure out what is the actual query to run and offer an answer. So we want to enable the same kind of behavior, but in streaming. So the question is like, it's super important. It's like this is the center of the pipeline here. However, the context of the question is almost as important. So I believe like the future of AI, so it's going to be the context. All this innovation that we see around agents and all this stuff is all about the context. So the data that we are processing and the metadata about the data, for instance, the schema of the data, provides a lot of information that's going to make the model give you very accurate code in order to answer that question. So you also want to have that. So as a side input for the question, this is not a problem. So one of the limitations of side inputs in an Apache Beam pipeline, a side input is a broadcast variable that gets distributed to all the workers at the same time. So it has to be small. It's small enough to fit in memory. But we're using a side input for the question. So this shouldn't be a problem. So the question shouldn't be really so long as to be a problem here, right? So it should be relatively small. So the prompt that we're going to be generating here, or the side input that we're going to be generating here, so it has these two different, let's say, conflicting needs. Okay, it needs to be small enough. Okay, it is small enough to fit in the worker memory. Small enough also for the model to be able to take it. So all the language models are going to have a limit here. So this is going to be probably a very large limit. Like if you want to use a model like Gemma 3 for open source, it has 128,000 tokens of limit as input. If you're using Gemini, this is billions of tokens. Okay, so I was super proud of my PhD dissertation. So it's 50,000 tokens only, really. Like, so you can put my full thesis in Gemma, and you still have half of the tokens to consume. So this is not going to be a problem. But at the same time, it needs to be large enough so you have enough context. Okay, so this is the side input for the questions. And this is how it physically gets executed. Okay, so this is here we see that when we have the different keys, the keys are processed in parallel. We have the window. Let's say the instance of the window for different keys is different, but the kind of window is the same. So we group the data, and then we ingest in every one of the workers the same question, the same side input in memory, and there are as many copies as workers we have in parallel, and then this generates the code, okay? So this is why, let's say, there's a vertical limit, because the window, all the data grouped together, and the question all together needs to fit in memory in each one of the parallel workers that we're executing. And this is how the prompt, so the prompt of the example that we're going to share with you, so this is how it works. The context, so this is what we put. Based on the schema and blah, blah, generate, and here in red, a SQL query. Generate whatever. Generate code that is pandas data frames. Generate generic Python code. Generate anything that you are able to run inside a Beam pipeline. And inside a Beam pipeline, you can run a lot of stuff. So you can run Python code for sure if you are in Python. If you are in Java with the JVM, you can run JavaScript code, for instance, dynamically. There are ways also to run dynamically SQL code, okay? And then we put here all the context, the schema. So from the window of data that we have, so we extract the schema, okay? It's doing some, I don't know, introspection on the data. We put some data into the prompt also. Here, three rows, whatever. It could be more because probably the model supports more, okay? So we put the data formatted in CSV. We put the question, and then the generated code. And the output of this is going to be code that we need to execute. But how can we execute this code? Well, this is another complexity for the pipeline. And this is, again, where side inputs play a role. So this is the complete pipeline, okay? So the pipeline wasn't completed before. This is the complete pipeline after we generate the code. The code itself is going to be also small. Should be small, right? So it shouldn't really be. The question is small, so the code, in order to answer that question, should be also relatively small. So we put that code in a side input as well. And we can have as many copies of the data as we want. So we had a branch with all the data in order to generate a prompt that had enough context as for the code to be good enough, to be accurate to answer the question. But we can just take another branch of the same data, and then now with code as side input, run the code and get the output. Okay, so this is the pattern that we apply in the pipeline, okay? Now, I'm almost done. Some word of warnings about side inputs. I don't like side inputs so much, honestly. I always have to sit and think about how I'm going to use side inputs in streaming, because it's easy to get it wrong. So when you have a P collection with a window, and you do a side input, what you are creating is a P collection view. There are different kinds of P collection views. You can have a list, you can have a dictionary, or you can have just a single element, a singleton. In this case, we are using a singleton because we have just one question or one piece of code that we need to run, so one single element. Now, when you have identical windows on the side input and the main input, easy, okay? Well, so things get joined in the same time context, right? But if you have different windows, here the difficulties begin a little bit. Okay, so there's a projection on those windows. And if you have triggers, for instance, in the side input, you are going to always use the latest value of that trigger, okay? Which is probably what we want to do here, because we want the user to be able to make new questions, and we don't want the users to wait until the window expires to be able to make more questions, okay? So we want to be able to react quickly to the change of the question. So this is what we want. So we need to define a window that is long enough as to provide enough, let's say, output for the question of the user, like, for instance, a window of 1 hour here. At the same time, as I said, the data needs to be small enough as to fit in memory. So here, for instance, a window of 1 minute, okay, whatever. The windows need to be aligned, okay? So 1 minute is a subset of 1 hour, so this is perfectly fine. And I don't want to have to wait for a full hour to change the question, okay? So there's another limitation here also that, well, the question will not be, let's say, lasting for more than 1 hour, okay? But now, once we have the question also, we can also take that code and maybe try to deploy a pipeline when the user is happy with the dynamic exploration of the data with their question, so we can take that and transform that into another static pipeline. Okay, so we are finishing. Conclusions here. So Beam is great for streaming inference. I think it's going to become much more popular than it is these days to do inference, especially in streaming. In batch, inference is kind of solved. In streaming, it's a little bit more difficult because it really simplifies doing any kind of pattern that you can imagine for inference. In the case of AI and dynamic transformations, the future of AI is context. Okay? There's a lot of investment in making the models be able to take more context for this. Okay, so I think this is going to be crucial, and this is a pattern that you can easily implement with Beam, like we have shown here. Okay, so here you have two repositories with the example. So the one in the GitHub of Fear is the specific example which is still work in progress actually. So where we are working right now. Okay, and in the other side you have the data flow solution guides, which are specific to data flow, but the pipelines that are contained there are generic Beam pipelines. Okay, so we took one of the data flow solution guides on how to use Gemma with a GPU locally in data flow to make the example that is in the second repo. It's an example that is use GPU locally with Gemma because the customer we were working with require running locally this pipeline, so they don't want to use a remote service to be able to call a large language model. But again, as you have seen, with run inference, changing from local to remote to anything, it's quite straightforward. So give it a try, and well, and we would like we would love to hear your feedback about these examples. Thank you.